Hey everyone, welcome to the Freezing Point Depression Lab lecture portion. Let's dive right in. So the first thing that I would just want to kind of bring to your attention, when molecules come tighter to form a solid, the process is called crystallization, freezing, or solidification. Now the reverse is going to be referred to as your melting or fusion. A liquid containing an impurity freezes at a different temperature than a pure liquid. That's kind of what we plan on investigating this time around. So this phenomena is largely driven by entropy. Entropy is the measure of your disorder in a system. That's any system, okay? It's entropy. Entropy, disorder. The more disorder in a system, the lower its energy and the more stable the system is. Think about it this way. It takes less energy to mess up your room or your house than it does to organize it. That's kind of how I reference it. Like I can come in from work, I can throw things on the couch, but then when I go to pick it up off the couch, it takes twice the energy to kind of go through it. Where does it belong? I have to think about it and all those things. So a liquid solution that contains a solvent with an impurity has more disorder than a pure solvent. Okay, a liquid solution containing a solvent with an impurity is more disorder than a pure solvent. So normally, if we're doing these lectures in class, I give you an opportunity to earn some bonus points. We're not going to have the opportunity to do that since we're going to watch this online. But I was thinking I could go ahead and give you the questions. You could create a tab inside of the freezing point depression section inside of your lab, right? Call it bonus opportunities, and then you can answer these questions and you don't have to bother turning them in. I can look at them the next time I check your notebook next week. So first question, here you go. What is an impurity? Number one, what's an impurity? Number two, what happens when a solution freezes? Number two, what happens when a solution freezes? Number three, what kind of state does this create? Number three, what kind of state does this create? And number four, is this true or false? Solutions of solvents with impurities freeze at a lower temperature than pure solvents. All right, there will be other opportunities for those. There's going to be more coming through. So let's just talk about this. You have a crystal, which is a solid, a solution, which is a liquid, and a vapor, which is a gas. So your liquid solution is more disordered than your liquid pure solvent, and it requires less energy to force the solid solution into its disordered liquid state than to take the pure solid into its liquid state. I'm going to go back to the front slide. This is where we said hello in the beginning of this lecture, but what I'm saying is the solution melts at a lower temperature than a pure solvent. The freezing point and the melting point are numerically equivalent. The phenomena of a lower freezing point for solutions compared to pure solvents is referred to as what? You can actually add that into your bonus section if you are participating. It has a property, and because of that, the magnitude of the reduction in the freezing point is proportional to the quantity of the impurity present. So what you're looking at is your TFP, or your pure solvent, minus your T or your solution, your T or your solution equals your change in temperature. Remember, your triangle T is your change in temperature between your freezing point of the pure solvent and the freezing point of the solvent in your solution. Here's another opportunity to add to those bonus points. What does Kf in the freezing point depression formula represent? What does that Kf represent? What does the M represent? And what is molality? How do you calculate molality? All right. So let's go back here. Sorry about that. My fingers got crazy. This is Van't Hoff. Okay, and Van't Hoff factor, which is the effective number of particles produced when a solution dissolves. You'll see that represented as a lowercase I in parentheses, maybe. And I'll show you when we get a little further into the lecture. 1 mole of sucrose, which is a covalently bonded molecule, dissolves in water, and 1 mole of particles is then produced. This just means that the molecule remains intact in the solution and no bonds can be broken within the molecule during the process of it going into solution. Okay, Van't Hoff factor. That's where we're at on that. If 1 mole of sodium chloride dissolves in water, the compound, which is your NaCl, it's going to dissociate into its ions, and they're effectively 2 moles of particles. 1 mole of sodium, excuse me, which is your Na plus, and 1 mole of your chloride, which is your Cl negative, which means the Van't Hoff factor is 2. Your lowercase I would equal 2 for NaCl because it's NaCl, 2 compounds, we're disassociating it, so there has to be 2 mole. All right, so last opportunity, I believe, for some of these is, all right, write the formula for moles of solute. Write the formula for moles of solute. Okay. This is another question. Molality is blank of solute divided by blank of solvent. Molality is blank of solute divided by blank of solvent. And then lastly, what can you use the freezing point depression equation to calculate? What can you use the freezing point depression equation to calculate? All right, so let's just assume that your Van't Hoff factor is going to equal 1. That's your lowercase I in parentheses. Your Van't Hoff factor is equal to 1. We can set up a formula just like this if our Van't Hoff factor is going to be 1. So this is just an example of what your graph should look like. You're going to make sure to put your name, the title of the lab, the trial number on your graph. I would suggest that you make sure to leave however many pages you need to accommodate your graph for upload into the PDF. What I'm saying is you're going to have a bunch of graphs, and all of those graphs are going to have to be at the tail end of your report to turn those in as PDFs. So let's just talk about what kind of steps we're going to have. This experiment is going to have 3 steps. Okay. First, you're going to determine the freezing point of pure lauric acid. All right. Then you're going to repeat all of those steps, and you're going to do that with benzoic acid added to a solute. What's a solute, right? Remember, what is a solute? And then lastly, you're going to obtain a fresh sample of lauric acid and use an unknown as a solute. You're going to do each step twice. I'd like you to do the first one and your partner to do the second one. You're going to average your results. So when you analyze the results, you're going to be able to compare the molar mass of benzoic acid to its known value in the literature, but not with the unknowns, and you're not going to be able to identify it using the info you've been given from the experiment. It's not expected, so don't rack your brain over it, okay? So accuracy and precision are critical to obtain useful data in this experiment. You're going to read the thermometer to your nearest 0.1 degrees Celsius, and this could prove to be difficult because it does move quickly. Just do the best that you can, okay? Your time intervals of your temperature measurements must be known accurately. Your time is much more important than your temperature. Now, they're both important, but we're going to do the best we can. The temperature is going to move quickly, but make sure one of you is watching the temperature, one of you is watching the timer, okay? So thank you for watching. I hope that everything goes well in the lab for you. Let me know if you have any questions, and I look forward to seeing you guys in lab.